In the last video, we looked at even power functions. Now I want to take a look at odd power functions. Now remember, a power function has this form, f of x equals a x to the n, where that coefficient a isn't 0 and where n is a positive integer. So I'm just taking a look at some very specific examples here. I'm specifying that I want n to not only be a positive integer, but I want it to be odd. And I'm looking, at least for right now, at power functions where the coefficient is just 1. Okay, I want to take a look at those graphs, see what I can say about those graphs, and then I know what multiplying by a number does. It's going to either vertically stretch or shrink things, and if a is negative, it would flip them as well. Okay. All right, now, if n has to be a positive odd integer, the first one that we would have is n equals 1. So I could look at y equals x to the first. Well, that just means y equals x. That's my identity function. That's a line of slope 1 through the origin. Okay. Now, that's the one sort of power function we're going to have that doesn't curve at all. As soon as the power gets bigger than 1, we're going to start having some curve to our graph. But this linear function, the identity function, is an example of a power function. And any multiple of it, any non-zero multiple of it, would be a power function as well. Okay, the next positive odd power I would have is y equals x cubed. And we're familiar with that graph because that was one of our parent functions in chapter 1. There are going to be 3 points that are on both of these graphs and that will be on the graphs of any odd power of x. Okay. So the origin, 0, 0. That's because 0 to any power is any positive power is going to be 0. 1, 1. Because 1 to any power is going to be 1. These 2 points were on the graph of our even power functions, of our even powers of x as well. Okay. And then negative 1, negative 1. Now that's new. Negative 1 to an even power would have been 1. That point was on the graph of any even power. Negative 1 to any odd power is going to be negative 1. And so these 3 points will be on the graph of any odd power of x. Now, if I multiply by a number other than 1, if I have a coefficient in front of this that isn't 1, then I won't have exactly these points. But if I'm just looking at one copy of an odd power of x, I will have these 3 points. Now, with x cubed, I know what that looks like. I'm going to just underline this in green and draw it in green here. That curved something like so. And I can actually notice a similar pattern here to what I saw with my even powers. If I just look on the right side of the graph, between 0 and 1, the bigger power gives me the smaller value. I think about 1/2. 1/2 to the first is just a half, but a half cubed is 1/8, which is significantly smaller. At 1, they're the same, and then once I pass 1, the bigger power gives me the bigger result. So, for example, 2 cubed is much, much bigger than 2 to the first. Okay. And then I've got over here sort of a mirror image, but with negative values. So the absolute value between 0 and negative 1 is smaller for the bigger power, and the absolute value is going to be bigger for the bigger power. Again, what that means is that the graph is flatter in this middle section, but steeper once we pass 1 and negative 1. And if I take a look at y equals x to the 5th, you can probably guess that's going to be very, very similar. It's going to have these 3 points between negative 1 and 0, and between 0 and 1. The graph is a little bit flatter, so it's going to be closer to the x-axis. To the left of negative 1, and to the right of 1, it's going to be steeper so that the bigger power gives me the bigger result. Okay, and pretty much all odd powers of x are going to look something like this. So if I have something like this, f of x equals x to the n, where n is a positive odd integer, I can say, well, first of all, this is going to be an odd function, which means its graph is going to be symmetric about the origin. So if I were to flip this upside down, the graphs would look the same. Okay. And another way of thinking about that is opposite input gives me the opposite output. Now, if I look at the end behavior, as x goes to infinity, as I go to the right, what's happening, all these arrows are pointing right and up. So as x goes to infinity, x to the n goes to infinity. That's actually the same for whether n is even or odd. Both even and odd powers get big and positive as I plug in something big and positive. But now I can say as x goes to negative infinity, x to the n is going to go to negative infinity. Notice, opposite inputs, big and positive, big and negative, give me opposite results. Okay. So when I'm looking at a power of x, it's important to know if I'm going to negative infinity, whether that power is even or odd. So if I had g of x equals negative 5 x to the 103rd, okay, I could say as x goes to infinity, well, what I'm going to do first of all is just look at the power. Any power, even or odd, as we go off to infinity, goes to infinity. But now I'm multiplying it by negative 5. That's going to do a vertical flip, and that's going to change the sign of the output. So I could say g of x is going to negative infinity. As x goes to negative infinity, now, because that's an odd power, just the power by itself would be going to negative infinity. But I'm multiplying that by a negative number. Two negatives are going to make a positive, so g of x would go to infinity. Because I can see, if I have a shape like this, if I do a vertical flip, then this part, instead of going up, is going to be going down, and this part, instead of going down, is going to be going up. Okay. So those are my odd powers, and basically, for the end behavior, if I know where the power is going, and that's going to be either plus or minus infinity, when I multiply it by a number, a positive number preserves that behavior, and a negative number reverses that behavior. And that's going to be true for all power functions.